we talked about naive Bayes. And with naive Bayes, what we were trying to do is we were trying to apply Bayes' rule and model the probability of seeing X given Y. So for example, given that the email is spam, what's the probability of seeing this feature versus not seeing it? And we were estimating those by counting things. And this is called the generative model, and it's a general strategy where you model how the data got generated, and then you use that to find the best class to predict. So we also saw logistic regression earlier in the course. So it's an example of a different type of general approach called a discriminative model. And in that case, what we're doing is we're directly modeling P of y given x. So we're not saying in logistic regression, this is how where the x came from. And when we're done training, we can't synthesize fake feature values because our model wasn't set up that way. Whereas with naive Bayes, we can do that. So it's a question of which probability distribution are we actually trying to estimate. And both of these things have their strengths and weaknesses. So let's try to reinterpret what was happening with logistic regression. Our model was the probability of the label given the features were the sigmoid function of W transpose X. So it was a linear classifier. We first took W transpose X. That was this raw output of the linear model. And then we passed it through the sigmoid function, which I'm calling H here, which said big values get mapped to 1, and big negative values get mapped to 0, probability 0, and values near 0, meaning near the boundary, get mapped to probabilities near 1/2. And by the end of today, we're going to have a new interpretation of this loss. So the interpretation of this loss so far was, here's a smooth-looking thing that behaves kind of the way we want, in that it's lower when you're getting the answer right and higher when you're getting the answer wrong. And that's all we really said about it until now. And we'll come up with a more precise interpretation in today's lecture. So we're going to be talking about the framework of maximum likelihood. And I guess the first question is, well, what does the word likelihood even mean? So I'd like to go with an example of just flipping a coin. So let's call the probability of heads W. And we can ask, what's the probability of seeing K heads in N tosses? And there's some sort of statistics probability prerequisite to this course, so I'm assuming most of you have seen the binomial distribution, which is the way you would model this coin flip situation. And this is what the binomial distribution says. It basically says we're assuming each coin flip is independent, so to get K heads, that's probability W times probability W. W, that's the W to the K. And 1 minus W is the probability of getting tails to the power of number of tails, and then some coefficient out front to make all the math work out right. That's the binomial coefficient. So this is a probability distribution, and its variable is K. So if we wanted to look at this thing, we'd say, OK, we're flipping it 10 times. What does this look like for K equals 0 through 10? And we could plot that or look at it for some given W. And it's just a regular probability distribution. It happens to be a discrete probability distribution, which means that it sums up to 1 instead of integrates up to 1. But nothing crazy going on here. And then the big question of today, and the mindset for you to get into is, but what if we don't know W? Because the binomial distribution is usually this tool of, well, I have a probability of heads 0.7. Now what are the chances of getting 5 heads or 7 heads or 8 heads or whatever? That's kind of the forward version of the binomial distribution. So let's say, to make it concrete, that we observe heads, heads, tails. So N equals 3, 3 flips. K equals 2, 2 heads. And then the question is, what do you think W was given that information? So do you think it's 0? No, why not? Anyone?
Probably 2/3 maybe?
Probably 2/3 maybe. Okay, but why are you sure it's not 0?
Oh, it can't be 0 because he's seen it.
Can't be 0 because we've seen the heads, right? So if W is 0, that means probability of heads is 0. That doesn't make any sense. Likewise, it can't be 1 because we've seen tails, and yeah, it's probably somewhere in there, right? So if we plug in N and K for the values corresponding to our data, and we'll use D to refer to our data and our training set as it'll become, but our observations, then the probability of seeing what we saw, which is 2 heads and 1 tail, is this function, but I haven't plugged in W because I don't know what W is. And probably the most important point one of 2 most important points maybe in the lecture today is this last line in green. In order to understand what likelihood is, it's just the same old thing, probability of seeing stuff given my parameters, but just thinking about it as a function of the parameters instead of function of the data. It's the same function, but we're in our mind just interpreting it differently. So we're using this as a score to say how likely is a particular W. And the logic kind of makes sense. If that W would have generated what I saw with high probability, I like that W. If that W had 0 chance of generating what I saw, I don't like that W. Any questions or comments about this? Okay. So on the next slide, I'll just copy and paste this equation back at the top. And let's think about what this thing actually looks like. Here is what this thing looks like. This is that function. I just plotted the function. And the interpretation of it, again, is it is the probability of seeing what I actually saw or observed, given different hypotheses about what W is. And it kind of behaves like we thought. W can't be 0. W can't be 1. And so the argmax of this function, the place where it's biggest, that's called the maximum likelihood estimate of our parameters. And yes, Oliver's intuition was correct. In this case, it's 2/3, or in general, K over N. I think the main misconception, the main thing that can go wrong is if you think of this as a probability distribution. So we're calling it a likelihood function because it is not a probability distribution. Well, it is and it isn't. This is really the key point. It is a probability distribution with respect to K for a fixed W. That's how we started. It's the binomial distribution. But once we said we're going to fix K at what we actually saw when we collected data and then just thought about varying W, then, I mean, you could look at this thing and say, well, even if it filled up the whole rectangle, that would be width 1 and height 0.5. So the area under that thing is definitely less than 0.5. Which means it's definitely not 1. And why should it be 1? This is not a probability distribution. Yeah, what's your name?
Lin.
Lin?
So we observe head tail in 3 flips, but it's not 2 heads in 3 flips. So why the probability should be multiplied by 3?
Okay, fine. We observed 2 heads and a tail. Yeah, we can ignore the ordering issue. It doesn't really matter. It doesn't affect any of this discussion. In fact, I mean, exactly to my point of this thing not being normalized, I'm only looking for the argmax of this thing anyway. So whether there's a 3 there or a billion or whatever, I don't really care. So any other questions? This is kind of the whole point of the lecture, and then the rest of it is just connecting this to stuff we've already done in the course. But it's not, it's relatively subtle, this thinking of it as a function of W instead of as a function of the data. Okay. So more generally, moving away from this coin flip example, we have some data set. We want to learn some parameters, W, and we define the likelihood as the probability of seeing our observation given our parameters. And then we pick the W that makes this thing as big as possible. So at risk of repeating myself, our score for how good a W is, the scoring function is, if this were the W, what's the probability of seeing the stuff that I indeed observed? And there's some nice justifications for doing things this way that we're not going to go into. Okay, now let's start connecting this to what we've been doing in the course. So we want to maximize this thing, the likelihood. And what we're actually going to do is we're going to minimize the negative log likelihood. So I'm claiming these two things are the same. And why are they the same? Oh, I went ahead too quickly. Okay, so why are they the same? Because, first of all, if we want to minimize something or maximize something or minimize the negative of that something, that doesn't matter. I mean, again, it'll change the value, but it'll not change the minimizer or maximizer. And if we want to take the maximum of the log of something, same thing. Since the log log is just a monotonic function. I guess my hand waving was not quite the right shape for log, but anyways. The W that makes this thing as big as possible is the same as the W that makes log of this as big as possible. So yes, we're changing the score that comes out, but we're getting the same W hat at the end by minimizing the negative log likelihood. Liam?
Is the original probability function?
Is the original function going to be monotonic? No. In fact, the one we looked at before wasn't, right? But that's...
Convex.
Oh, is it going to be convex?
Yeah.
Well, it depends, right? It depends on the model. So we will see some examples where it is, because we'll see how this corresponds to things we've already done. Okay. So the nice thing about taking the log, I mean, I told you it was allowed, but I didn't tell you why we want to do it, is that we're assuming all our observations are IID. So we've seen a bunch of samples of something. And so the probability of that is the product of the probabilities of the individual cases. So I've observed 20 things. What's the probability of that? Well, it's the product of each of those individual 20 probabilities. But now, because we're taking the log of the whole thing, this log of a product turns into a sum of logs. And that's what this last line is here. So we're trying to find the W that maximizes this product. That's the same as trying to find the W that minimizes negative sum log of those individual terms. Any questions about that? Arman?
How does this relate to like information gain?
How does this relate to information gain?
Like entropy? 'Cause the formula could be very similar.
Yeah, I'm going to punt that question for the moment. Okay. So what we end up maximizing is different in these two general categories, generative models and discriminative models. In the discriminative case, we're not modeling the features or where we came from. We just consider those to be given to us. And so all we're really trying to do is maximize the conditional probability of the outputs or the labels. So what we're actually getting in supervised learning, which is what I'm getting to, is these XY pairs. But we're just considering in these discriminative models, the X's are just given to us, and we just want to model what happens to Y. And now we get into punchline number 1, which is, as I mentioned before, we want to minimize the negative sum of these log probabilities. In the logistic regression case, where do these probabilities come from? Where our assumption for logistic regression is that the probability of seeing a label plus 1 is the sigmoid of W transpose X, or negative W transpose X. So with logistic regression, we're directly assuming what this relationship is. From features and W's to probabilities, we just said, this is it. Given X and W, that's how the probability comes out. And so we can plug this into our general framework of minimizing the negative sum of the log of these probabilities. So I can just plug that in right here. This probability from logistic regression. And then I can flip the thing inside of the log, which pulls out a negative 1. That cancels the negative 1 that I already have. And then I end up with the loss for logistic regression. So to summarize, when we first introduced logistic regression, I said, we said, let's talk about linear classifiers. We would love to minimize the 0, 1 loss because it tells me how many errors I'm getting, but I can't minimize that 0, 1 loss because it's not smooth, convex, all those things. So I just showed you this logistic loss, and I said, oh, that looks like a good idea. It points in the right direction. Why don't we just do that? And I said, oh, and by the way, on an unrelated note, you may be interested in turning these things into probabilities. We need some sort of function. Again, I just described some properties. We want a function that takes small numbers, maps them to things near 0, takes big numbers, maps them to things near 1. And we said, OK, this kind of S-curve shape makes sense. So let's turn our numbers into probabilities using the sigmoid. But what I'm saying here is that those are not two arbitrary choices, and that I'm kind of changing the order on you. Instead of first introducing the loss, I'm saying we could think of our fundamental assumption as this probability thing. We're starting by assuming this is our probabilistic model for how the y's are generated. And again, just the y's because this is a discriminative model. So we're actually going to start by saying, I believe where my y values came from is that I took that particular x, took a dot product with some w that I'm trying to find, and then stuck it through the sigmoid thing, and then flipped a coin with that probability p. And that's where that thing came from. And if that's my initial belief, then the right thing to do, if I'm doing maximum likelihood, if I just follow that to its logical conclusion, then I should minimize this function to get the right W. And I'm not saying maximum likelihood is always the best thing, but if we do maximum likelihood, which at least has some justification behind it, then I can't just pick any curve thing. If I'm saying my probabilities are that, then I should minimize this. Any thoughts on that? I mean, if you just want to download scikit-learn and fit stuff and predict stuff, I guess you can live without this information, right? But we're going a little bit deeper in this course and presenting a different angle on things we already did. And we'll continue to do that today. Okay. I guess I've said all of this. So MLE, by the way, maximum likelihood estimation. Okay, so let's now reinterpret least squares. We've already reinterpreted logistic regression, why not, right? So we've been minimizing squared error, and we didn't really have a justification for it to begin with, except it's very easy to minimize. That was the justification we started with. It has this nice gradient that is a linear function of W, and it's easy to solve gradient equals 0. But let's play this same game again. Let's say, actually, we're going to start by assuming that where did our y values come from? I'm going to assume that for every x, there's some unknown w. I would like to find out what it is. That's the whole thing I'm trying to do here, is find out what it is. But whatever it is, it got dot producted with that x. And then there was some Gaussian noise added to it, meaning some IID Gaussian random number got added to it. And that's plunk, a point on my graph that I observed, right? So if I truly believe this is where my data set came from, then I can show, and will show in a second, that if I want to find the maximum likelihood estimate of W, which is, again, the W that makes the data set I observed most probable, I actually need to minimize this squared error. Okay. Bit of a messy slide coming up, but we can work through it. Okay, so we need to figure out what is our probability of y. That's where we started last time with logistic regression. Probability of y is W transpose x passed through a sigmoid. Well, in this case, our probability of y is a Gaussian distribution centered at W transpose x, because we just said it. We take W transpose x, that's some value, then we add a Gaussian noise to it. So that's the same as Gaussian centered at that point. So this thing at the top is the Gaussian distribution, or the simplest version of it. And probably most of you have seen this before, or all. So my probability of yi, again, given xi, assuming that's fixed, is the Gaussian distribution centered at W transpose x. And now, again, we need to get into this mindset, right? I don't mind repeating it a bunch of times. I think it's important. When I look at this on the slide, I'm like, that's a probability distribution for y. It's telling me where does y come from. But we are going to reinterpret that function as a function of w and be like, oh, well, actually, I know y, or I know n of them, x, y pairs at least. I've seen this happen n times. Let me fix that and just ask, well, what is the value of this function for different w's? It's just the same as what we did for the coin flip, but it's messier here because, well, for one thing, w is a vector. But we're still using it as a score for w vectors. And then we just have to crank through the whole thing again. We know we want to minimize negative sum of log of that thing. Okay, just plug it in again. Negative sum log of, I'll just plug this thing in, and then it's all just algebra from there. So first of all, the 1 over 2 pi gets pulled apart by the log, and we don't really care about that anymore because it doesn't involve w. Okay, then we have log of x of something. Those obliterate each other. And we get negative sum, some constant thing that we don't care about that came from the 1 over root 2 pi. Minus, that's this minus sign moving over there. And all that stuff I was exponentiating. And then the sum of a constant is still a constant. I mean, I would have been happy getting rid of that even earlier. But if you want to be careful and really keep it around, you keep around the constant. You just ignore it at the very end. And you end up with this least squares, or this squared error. So now if someone asks you, why are you minimizing the squared error, you can say, oh, it's because I believe the y values are Gaussian distributed around w transpose x. And I think maximum likelihood is the right thing to do. And neither of those are probably actually true. But it's OK, right? We've seen this throughout the course, that frameworks of thinking about things are useful even if we violate those assumptions, like with naive Bayes and many other times in the course, the IID assumption, etc. Cheyenne?
So,
Is that right?
yeah.
OK.
So what if I change my loss function to the absolute?
Ha ha ha. OK. Hopefully that's the next slide. It is, right. It's the next slide and my favorite part, I think, of the lecture. So what if I change my loss function to absolute value? What does that mean? What assumption did that correspond to, right? Well, you can kind of undo all that algebra I just did, if you will, and work backwards from having the absolute value loss. And you find that your assumption is this so-called Laplace distribution. Instead of e to the minus something squared, it's e to the minus absolute value of something. And here's the amazing part. Okay. The amazing part is let me get the other color. These are two different functions, okay? They're both probability distributions. You may have heard the term, this distribution has long tails or short tails or something like that. What does that mean? Well, taking e to the minus something is a pretty extreme thing to do to a number, right? Taking e to the minus that number squared, that's bam, right? If I plug in even like 10, that's e to the minus 100. I don't know what that is, but it's really small, right? So this thing goes to 0 very fast. And that's why you might say this is a short-tailed distribution. Because even when you move away from 0 a little bit, you're just doing this ridiculous operation to that number, right? This is a little more mild. At least you're not squaring the number. At least you're taking e to the minus 10 instead of e to the minus 100, which is a big difference. All right, just think of 10 to the 10 versus 10 to the 100. One's like a number you've heard someone use, and one's like unfathomably big, right? So here is where this all comes together. This corresponded to our squared loss, and this corresponded to our robust loss. Why? Because if this distribution goes to 0 very fast, it means by assuming this, you're very unwilling to believe in big deviations from your mean, which is your regression curve in this case, your W transpose X. If I have just in one dimension, if this is my line and I have a point over here, and this distance is 10 or whatever, some big number, what's the probability that I would have seen that? Ridiculously small, right? Because this distribution is going to 0 so fast. So by picking the Gaussian as your assumption, you are saying, I just can't believe you'd ever be that far from the line. Which means, if I have a point over here that's far away, I would rather pull the line so that I have a less unbelievable thing, a deviation. Because I just can't get over here. That number is so close to 0 that the total probability gets incredibly small. This guy's a little more forgiving. It says, yeah, I could see that happening. You know, my probability is not going to 0 if you're this far away. Maybe it's 0.01 or whatever. It's small, but it's not ridiculously small. So there's no need. Remember, we're using this probability and thinking of it as a function of W. So when choosing what the best W is, we're trying to maximize that. So with the Gaussian, I do not want to be very, very far away from any particular point, or my score is going to contain a number that's very, very small that I'm then summing together or multiplying together. So this is another interpretation of this robustness property, that the absolute value loss is robust and the squared loss is not. The other interpretation is this corresponding distribution has longer tails. It's not as freaked out when something's very far away from the mean, meaning the regression curve. And so it allows for those bigger distances, whereas the squared error doesn't. Time. Any thoughts on this discussion? Questions? Okay. When I first saw this, it was quite an amazing moment. I don't know if anyone's feeling that, but anyways. Okay. So let's now critically consider maximum likelihood and whether it's a good idea. Maximum likelihood says we have this probability thing and we're going to use it as our score for W. So I'm fine with whatever W makes the data most probable under that W. But what if we thought certain W's just made more sense than others before we even started? Like what if in the coin flip situation, I thought it would be ridiculous to have a coin that was always heads? I mean, how is that even possible, right? I don't know. I mean, it's not very likely, right? If the thing looks like a coin and one side of it says heads and one side of it says tails, it's probably going to land on heads sometimes and tails sometimes, unless there's some crazy magnet thing under the table or whatever. So actually, I think W is probably around 0.5, and there's probably just a slight imbalance in the coin, and maybe it's 0.45 or 0.51 or whatever. But if you just showed up in my office and gave me a coin and flipped it twice and said it was heads both times, therefore W is 1, I'm going to say that's ridiculous, right? And yet, that's the maximum likelihood estimate of W, seeing heads twice, or even once. Just seeing heads once, your best estimate of W is 100% heads. Something's wrong. So what we want to do is we want to introduce prior information about W. We want to say, I have some thoughts about what W's make sense and don't before you show up and flip the coin. And now we're back to this Bayes rule business. This prior distribution is this P of W. If we multiply P of W times the thing we've been dealing with earlier today, namely P of D given W, Bayes' rule tells us that up to a proportionality constant, that gives us P of W given D. So let's directly say what is the probability of W. That's actually what I want to know. That's what I want to be biggest, and that has two parts to it that are getting multiplied together. The part that's coming from the data, and the part that's coming from my life experience flipping coins or whatever, right? So what's nice about Bayes' rule is that it's intuitive that both of those things should contribute, but it's saying the way they contribute is you just multiply them together. That's nice. I can do that, right? I know how to multiply. So here's the fun part. We can do all this thing with maximize this is minimize negative log of that. We just play that game again. And what we get is the best W is, well, first of all, I said we were multiplying two things together, the data part and the prior part. As soon as we take the log, that becomes adding two things together, right? Log of the data part plus log of the prior part. So we have two separate terms, the exact same thing we had before, and the new thing. And what's wonderful about this is we just came up with an interpretation for our loss functions, but now we also have an interpretation for our regularization, which is some random thing we declared would be useful to mess with our loss function to not minimize training error, but to minimize training error plus something that we hoped would be a good idea. That's what we were doing, right? And it was a good idea. I'm not saying it wasn't, but it was a little arbitrary. But we can now interpret that regularization as a prior distribution, and all the same math follows. So for example, if you assume each W is IID Gaussian mean 0 with variance 1 over lambda, well, what is negative log of that thing? It's again a Gaussian. The log again, you get the multiplying becoming summing, you get the log canceling the exp, and then at the end of the day you get our good friend L2 regularization. Okay, let's try to interpret that. Well, my prior belief, if I'm doing this Gaussian thing, that means my prior belief is that the W's are centered around 0. They're Gaussian distributed around 0. So in other words, I kind of think W is going to be, before seeing the data, I kind of expect W to be near 0 rather than huge. Well, that's what regularization does, right? It's messing with the loss to make 0 more attractive than some giant number. And we can get intuition about this variance thing, right? What if this lambda is huge? That means my original Gaussian for my prior on W has a very tiny variance because lambda is big and variance is 1 over lambda. That means I believe W is some very tiny Gaussian around 0, right? It means this. So I'm really, really, really not happy about big W's. I think they're just ridiculous, right? My prior belief on them is extremely low probability. But bigger lambda also means more regularization. We've been doing that for weeks, right? So narrower prior means I'm pretty sure it's near 0. I'm pretty sure it's not way out there. That has mathematical equivalence to bigger lambda, which says try really hard to focus on this term, forget about the other term. That's how we've been thinking until now. So there's this very nice connection between not only the losses, but also the regularizers and all this probabilistic stuff. And again, the L1 regularization corresponds to this Laplace distribution prior on W. Okay, so there's a word here, or an acronym, I guess, MAP, maximum a posteriori. And it just means MLE, maximum likelihood, means take the argmax of that one thing. And MAP means take the argmax of those two things multiplied together, the original thing times the prior. So going from MLE to MAP, you're just incorporating this extra thing. And for those of you who've done more Bayesian statistics and that kind of stuff, you've probably encountered the fact that the prior tends to matter a lot when I have very little data. Like if I have 0 data, then it's all the prior. That's all I have, right? That's my posterior. But the more data I have, that's more evidence. The prior becomes less and less important. And we see that mathematically here, in that you're summing up a bunch of things. And the regularization, we talked a little bit earlier in the course about should lambda vary with n, but we hardly touched on it. But roughly speaking, I'm summing more and more things as I collect more data, and eventually this is going to kind of overwhelm the regularization, which makes sense because regularization is just supposed to prevent overfitting. Overfitting is just a symptom of not having enough data, and so I don't need to try as hard to prevent overfitting if I have more data. Edwin.
Are we using the probability density function to approximate the actual probability of W? Isn't the probability of W actually an integral over the density function? And the probability of W being a specific value.
Okay, when I write this notation like P of W, I'm referring to the probability density for a particular W. It's not an actual probability like 0.2 or something. It's just a density. Cheyenne?
Why is the assumption that W follows a Gaussian distribution?
Yeah, why would you assume that W follows the Gaussian distribution? So I have to agree that's a tougher sell than the loss part. Because, yeah, the points are Gaussian around some line. Like, that could happen, right? But as far as the prior is concerned, okay, the whole language of probability is kind of used in two ways. It is used to model things that are random. Like, if I do it a million times, it'll be different every time, and I can generate a million things, and then I can see, was I right? Like, did it follow the probability distribution that I thought, right? So if I had infinite data, I could say, was I right with this Gaussian thing? Like, I draw the line, or it's a plane in higher dimensions, and I can just look at how far are my thingies from the plane? What do my residuals look like? I can make a histogram, and it might be Gaussian, or it might not, right? But the other way that probability is used is to talk about uncertainty. And they're a little bit different, because you might have a thing that's actually random, or you might have a thing that isn't random. It exists, I just don't know it. And I need a way of talking about how I don't know it, and then I use the exact same language of probability. It's a bit of a subtle distinction, but the prior falls into that other category. I mean, there isn't exactly like the true prior. I mean, the prior is just a way that I'm encoding what I believe, right? And yeah, what I believe could turn out to be wrong or right. to lesser or greater extents. But it's harder to assess, like, was that okay or not? So priors in general, they're complicated. It's hard to come up with reasonable ones. Often they're just chosen for computational reasons, like I know how to get the W if I pick this prior, so I'll just pick that prior, right? So I wouldn't worry too much about the shape of it, other than to the extent we've talked about. Like the fact that it's centered at 0, that's the same as regularizing towards 0. Like I never wrote my L2 regularization as like W minus some vector. Like we could have regularized like this and said W needs to go towards some vector, but we always pick this to be 0, right? So because we thought smaller coefficients were better, that represented simpler models, and we observed overfitting corresponding to big W. So I can justify centering my prior at 0, and then I can't really justify making it a Gaussian any more than I can justify using L2 regularization. It was convenient and got the job done. I guess that's the best answer I have. Okay. Many of our loss functions and regularizers have probabilistic interpretations, indeed. There's this correspondence between the likelihood and the loss, and the correspondence between the prior and the regularizer. This is a wonderful opportunity to get things confused, so try not to, right? Already people always get confused between L1 loss and L1 regularization. Every year this happens. Now there's this like additional matching of this one and that one and this one and that one. So try to think through the intuitive arguments we talked about to keep those straight rather than memorizing them if you can. So those arguments being the likelihood distribution is like, where does y come from? How like could it be really far away or not, or all those kinds of things? And that's kind of what the loss part does, is it penalizes being far away or not or whatever. And the prior is like this arbitrary thing that I just said, oh, by the way, here's what I believe before I start. And the regularizer is also this arbitrary thing that neither of them has anything to do with the data. It's just this extra thing. Okay. So today we focused on discriminative models. We didn't really say anything about generative models other than they exist and they have something to do with naive Bayes. That's okay. We restricted ourselves to linear models. I mean, you wouldn't have to do that, but we restricted our discussion today of, in other words, you could think of W transpose X giving you the mean of the distribution, if you like to think of it that way, or I believe my Y came from W transpose X plus some noise. You can think of it that way. There's many ways to think about it. We talked about maximum likelihood as a new viewpoint of stuff we've already done, and maybe got some extra intuition about robust versus not robust losses. And then we talked about map estimation, where you use not just maximum likelihood, and I gave you that coin example as why maximum likelihood could be a little broken in some sense. I guess one thing that maybe I cut, but at least worth saying is you can also interpret Laplace smoothing from naive Bayes as a prior. And if you're interested in that, I think it should be in the bonus slides. And if you're not interested in that, that's fine. Okay, that's it for today. Have a great weekend.